Right, so this is the second part of this video number 5, where I want to talk a little bit about skeletonization and trying to get the essence of the shape of the underlying vascular tree. So just to remind ourselves, in the first half, we talked about a method for chopping up this vascular tree into different territories, right? So the anterior, the medial, and the posterior cerebral artery territories using a template that I found online. And so for this second one, sort of another useful idea that might be that you could explore is trying to figure out what the actual shape of this complicated object is in 3D. And so one fundamental idea from image processing is that you're not actually interested in how thick it is maybe at the start if you're just trying to establish how things are connected. What you're trying to figure out is sort of the skeleton of the underlying shape, okay? And there's actually an image processing method called skeletonization. So if you Google around for that, so I just found this one at Informatics webpage from Edinburgh where they explain this in a bit more detail. There's a couple of Wikipedia articles on this stuff as well. And you can see how this method actually works. Now, I'll walk you through some MATLAB code that I downloaded from the file exchange. So let me just close this window down here. So in the shared folder that we have for the MSc project, I've already done this, so you don't need to repeat this. So there's two functions here that I found, which were actually also selected by the MathWorks as an example of good code. One is called Skeleton 3D in MATLAB, which you can download from this GitHub page. And another one, which we'll come to use as well, is how you can actually turn these skeletons into something called a graph, okay? And maybe not a graph as you know from plotting a time series or sort of trace over time, but in a sort of more special mathematical meaning where we're thinking about these objects that have certain points or vertices that are connected by nodes, okay? And you will hopefully come and see how this is useful for establishing the shape later on. So I've already downloaded those. You should be able to see them in your MSc file. If you want to make sure that you can add them to your path, I do add with subfolders using the path tool here. I've already done this before, so for me these things are located in my home directory in a folder called the University of Nottingham, which is where 2019, and I've put the MATLAB code in there here. So if you add this MATLAB code folder with subfolders, then you should be able to have access to the code. Otherwise, if you have a slightly different setup on your machine, just make sure that MATLAB has them on the path. Okay, so I've already done this. I'm not going to do this, but you should either try save or close and just use it for this particular session. Okay, if this has worked, you should be able to find the functions skeleton 3D. You can get help on it. It basically gives you a short description and the references for how this was used. But in that folder, there's also some example code. Okay, so I'm just going to go and find out where that is actually located. Which skeleton 3D are you using? So it's in this place here. Okay, so that seems like the right thing. So you'll have something very similar. There's a sample script which is called test underscore skeleton 3D, which we can actually open up. Okay, edit. Right. So if you want to run this, you actually need to go into the folder where this file is located so that MATLAB can load in this test volume, which would allow you to make these particular figures. But what I'm going to do is I'm going to actually use this sample code and sort of retrofit it with some data that we already have. Okay, so I'm just going to transplant instead of using their sample data. I'm pretty confident that the demo would work if I just tried it, so feel free and go and test that out yourself. But I'm actually going to try and turn our angio data, or maybe the vessel probabilities one, which is sort of a slightly more smoother looking object, which is slightly more chunky, and see whether this is going to work. Okay, so in here what I'm going to do is I'm just going to start modifying this file. So I'm going to say this example script for exploring skeletonization. Okay, I'll add my DS 2020 sometime in July. Okay, and I'm going to try and save this as, and rather than doing it here, I'm going to go to the local folder where I have, so I've made a little subfolder here in my MSc project folder where I'm keeping the data called Skell, just to explore this. And I'm just going to, instead of calling it test skeleton 3D, I'm going to make sure that we know it's ours. I'm going to call it angio skeleton 3D. Okay. You could put in some information here about this code is based on the example in test underscore skeleton 3D. Not because we're worried about stealing the code so much actually, but also just for us to be able to reconstruct what we did. Okay, so let's go through this here. So clear all, close all. I usually don't do this in my scripts because I don't want to. I want to make sure that I don't actually accidentally delete some stuff. So I usually do this by hand. So we can delete those guys here. Make a comment here. This is where the data get loaded in. So we need to fix this load statement here. Okay. So the first thing we need to do is actually look inside our folder. I have copied across AngioBrain, the angiogram in the native space, and the vessel probabilities file. I'm actually going to start using this one here, the vessel probabilities, because I think that's going to look nice. So how can we load, instead of a MATLAB mat file, a Nifty file in? Well, think about this for a second, right? You should have hopefully done this by now quite a few times. So I'm going to actually say, I'm going to use data is equal to Nifty read. And here I'm going to decide which file I'm going to load in. Okay, so as per sort of good practice, maybe rather than hard coding a file name, I'm actually going to make a variable that contains this file name. And I'm just going to pick vessel probabilities.nii.gz. And then if I decide I'm going to change the file that I want to load in later on, I can just change this or even turn it into function or whatever. Now, another useful thing is to get some information about these images for voxel sizes and so on. And for that, we can use Nifty info. And now we can just use this, reuse the same variable here. Now, let me just make sure that this actually works. So I'm going to jump over to the command window. Nothing in my workspace, so whos would tell me if there's any existing variables. So if I go over here and I have mistyped anything, if I run this section, it should load in the data file. So it's busy at the moment, as you can see in the bottom here. Move this up a little bit. And if I repeat whos now, you can see that we've loaded in a data set, which is relatively big, right? It's got lots of rows, columns, and slices, and also there's some header information about the actual image. Okay, and so in this test_vol mat file, there's actually a variable called test_vol that I know was an image that contained logical values. So 0 where there's no voxel of interest, and 1 where there is a voxel of interest. So we may have to convert this thing here as well. So we could just check in the help for skeleton 3D what's required. It basically says image returns the skeleton of a binary volume image. Okay, so we need to make sure that our image is sort of a binary image that doesn't contain lots of different intensity values between, say, 0 and 100, as is in universal probabilities. So I'm going to have to make a decision here how I'm going to do that. Okay, so I'm going to say turn data into a binary image. And so there's a couple of things you could explore here. Simple thresholding. So maybe anything that's bigger than, say, 10 or something like that, right? Or actually in the probability images, things work slightly differently, right? Because the higher numbers mean that you want the higher numbers mean more conservative, so they're actually more restrictive, I think. So we need to think about that for a second. But you could also explore something more complicated. So if you had the actual angio data and you wanted to turn it into this nicely segmented MR angiogram, there's some other image processing methods that come with MATLAB that would allow you to isolate these high probability things, okay? So the high intensity things there, so we can think about that for a second. But for now, let's just create a variable called test_vol that is the data, but only where the data is where the data values are bigger than 10, and see what happens with this. Okay. So I'm going to do this here. So we could see what test_vol is like. So test_vol is a oh, actually this doesn't work, right? Because this makes one big long vector. So let me just think about that for a second. So we don't actually want to do this. We don't want to index into it. We just want to actually get the binary image. Okay. So hopefully that will do the right thing. Yeah. So this has now got the same dimensions. So this does this comparison whether the value is bigger than 10 at every location in the voxel, and it preserves the original size of the matrix. Okay, so make sure we don't end up with an object that's the wrong size. So you can see that the original data file and the binary image test_vol that we made are comparable or in the same space. We can now actually use the volume viewer maybe just to look at that we didn't do anything silly here. So volume viewer comes with MATLAB. Yeah, and it sort of looks like we have isolated something here. So we could maybe double check that if we made this number a little bit bigger, so say bigger than 50, it's pretty quick, so the threshold is a bit more conservative, and see, so I'd expect the angiogram to be a little bit sort of more narrowly defined, possibly. Yeah, okay, all right. But maybe 10 was a good number, okay? Because so you can see here the carotids coming up through in the template, but I think maybe I want to actually have a little bit more, sort of be less conservative. So I'm going to switch this back to 10, okay? So we now have, just to convince ourselves that this is acceptable, right? We're somewhere here. So this is the complicated shape, this complicated object in 3D, and we now want to figure out what is actually the essence of the underlying shape. What's the skeleton of this? Okay, so that's going to be the next step in this thing, and we can just go through and see what the different bits of code appear to be doing. So I'm going to remove this, right? So this actually creates the skeleton. So use the code to create the skeleton. Okay. And so what is the skeleton, right? The skeleton is busy, it's going to take a while. don't know how fast this algorithm actually is, how much it gets slowed down for much bigger data sets, but there's lots and lots of voxels in here, so it's maybe not surprising that it takes a little while to go through and find out the one voxel contour that describes the shape on the inside this skeleton. Alright, so that happened, and you can see here it's got the same size, the same dimensions as the original cube, and we could also try and look at it, volume viewer of the actual skeleton. And sort of get a reality check here. It looks like there's, actually we can zoom in with the mouse. You can see it looks like it's a one voxel thing here that the rendering makes it broken a little bit, but it's sort of a one voxel shape that describes the connection, the sort of layout of this particular shape. Okay, so maybe this is a sort of an interesting way to go. All right. Just having second thoughts here about, so this still looks quite complicated. So maybe what we want to do is actually start with a slightly faster to compute skeleton. So if I do go back and turn this to 50, and actually I will add a tick and a tock, so we can see actually how this works. So if you have fewer voxels in your binary image that are active, then the resulting skeleton will be less complicated. And so maybe that's a desirable thing to have at the start. So this actually only took 17 seconds, whereas the other thing probably took a little bit longer. So let's have a look at this skeleton here. Right, and you can see some voxels here. This is a much simpler shape. So this is something you could explore in your. So these are the one voxel sort of spine of the geometric shapes that are present here. Okay, and this is a little bit hard to see what's actually going on, but it's a useful representation because in this next step we can turn it into this graph object. Okay, so this is actually where the business is happening here. And just as a note here, could use volume viewer to look at this. But they've actually given us in this example script another way of looking at the data as well, which I think might look quite nice. So this just creates a new figure, defines some colors. It uses the MATLAB function patch to render things in 3D. So I think what I'm going to do is I'm just going to try and run this cell, this section, and see what happens. So it shows some of the original data, which is stored in this test wall, this thresholded binary image, and on top of it, it will superimpose this skeleton using a 3D plot. So you can actually appreciate how these two things connect together. Okay, so here's this object in 3D. So let me just manipulate it a little bit so you can actually see what's going on here. So I think the easiest thing to see is probably if we, so this would be a side-on view, and let me make this a little bit bigger as well. If I manipulate this down here and rotate it, you can probably see that these look like they're the carotid arteries that are coming up, and I can zoom in a little bit here as well, so you can see better what's going on. Switch back to the 3D rotation. So the see-through gray area here shows you sort of a shrink-wrapped surface of this binary image, and the red symbols that are connected up here show you the skeleton of this shape. So the central spine that runs through this. Okay, so it's not quite the same as the center line in this VMTK toolbox, but it will do something very similar. Okay, So I'm going to stop the recording here. And in the next step, what we're going to do is we'll see whether we can actually say something about how connected those things are in 3D by turning this into sort of a more abstract representation of how things are connected. But when I do this, I want to also show you a diagram of what I mean by a graph and nodes and vertices. So we'll come back to this in a minute. Okay, so I'll stop the recording here.